Have you ever opened a giant spreadsheet and just had that feeling, that sinking feeling that this is a disaster waiting to happen? Well, today we're going to take that exact kind of chaos and turn it into pristine, beautiful clarity. We're diving deep into a core data engineering concept called database normalization. And the best part is, we'll be using a real-world university assignment as our guide to break it all down.
So, here's our game plan. First, we're going to diagnose the problem, figure out what makes the original data so messy. Then, we'll go over the rules for tidying it all up. After that, we'll walk through the cleanup process step by step, the real foundational work. We'll even touch on some advanced techniques for future-proofing. And then, for the grand finale, we'll prove that our new super clean system can do everything the old one could, but a whole lot better.
Okay, let's get into it. The source for this whole project is a data file with almost 50 years of unemployment statistics. I mean, it is packed with valuable information, but the way it's structured, well, that's where the problems begin. It's a classic example of data that just isn't fit for a reliable database. And here it is. This is what we're starting with. See how every demographic group, white, black, men, women, gets its very own column? This is what's known as a wide format. And look, it's fine if you're a person just glancing at it in a spreadsheet, but for a database, a system that needs to answer complex questions and guarantee that the data is accurate, this design is a minefield.
The assignment actually spells out the three big flaws here. First, you've got redundant data. That year and month is just typed in again and again and again. Second, you have what are called repeating groups, those demographic columns. That's a classic database design no-no. And third, there's something tricky called a transitive dependency. Take a look at recession status. Does that status depend on the unemployment rate? No, of course not. It depends on the date. It's an indirect relationship, and those kinds of relationships can cause all sorts of errors and confusion.
So we've seen the problem loud and clear. Now let's talk about the solution, which is actually really elegant. It's a process with a formal name, normalization.
At its core, normalization is just about creating a logical filing system for your information. It's about breaking things down into their smallest, most sensible parts. The goal is to get rid of all that repetition and make sure that every single piece of data has one and only one home. You do this, and your database becomes way more efficient, easier to update, and, most importantly, it becomes trustworthy.
Okay, time to get our hands dirty. The real workhorse of this cleanup happens in three main stages, known as the first three normal forms. This is where we lay the foundation for our new rock-solid database.
First up is, you guessed it, first normal form, or 1NF. This step goes right for the jugular. It directly attacks that repeating groups problem we saw, all those separate columns for each demographic. And the solution is a really clever move called an unpivot. Basically, instead of having one wide row with a column for every demographic, we're going to flip it. We'll create lots of shorter rows, and each new row will represent just a single observation. One date, one demographic group, and its one unemployment rate.
And here's what that looks like in practice. Just look at the difference. On top, you've got that messy, wide format. And after we unpivot, you get this clean, long format at the bottom. See how every single row has the exact same structure now? We haven't lost a single bit of information, we just organized it into a way more logical and scalable structure. It's a total game changer.
All right, on to the next level. Second normal form. Now, in our new table, the thing that makes each row unique, the primary key, is the combination of the date and the demographic type. 2NF is all about dealing with information that doesn't need that full key to make sense.
Just think about it for a second. Let's say we want to note that the demographic white falls under the category of race. Does that fact depend on the date? No, not at all. It only depends on the demographic itself. So we do the sensible thing. We give that information its own home. We create a separate demographics lookup table just for it.
And just like that, our one big table becomes two smaller, more focused ones. We have our main rates table, and now this lean, efficient demographics table that just holds info about each group. We link them together with a simple ID, which is so much better than having to write race or gender thousands and thousands of times in our main table.
And that brings us to our final foundational step, third normal form. This one is all about hunting down those sneaky transitive dependencies we talked about, where some piece of data depends on another piece of data in the row, instead of depending on the row's actual key.
This little diagram shows that chain of dependency perfectly. In our data, the quarter is determined by the month,
and the month is determined by the date. See that extra hop? The quarter doesn't depend directly on the primary key, it depends on the month. That's a transitive dependency. And it's the same thing with recession status. That's a property of the date, not of the unemployment rate for that specific row.
So you probably know the drill by now. We follow the exact same elegant pattern. We round up all these time-related attributes, year, month, quarter, recession status, and we pull them out into their own dedicated table. We'll call it a time dimension table. And now we're left with 3 beautifully clean, purposeful tables. One for rates, one for demographics, and one for time.
Now, for 99% of cases out there, those first 3 normal forms are all you'll ever need. But this assignment wants us to look ahead, to really future-proof our design. So let's take a quick peek at the more advanced forms. You can think of 4th and 5th normal forms as the expert levels. 4NF is about handling situations where you might have multiple independent facts for one thing, like if you were tracking multiple reporting agencies and multiple funding sources for one data point. 4NF makes sure you store them separately so you don't create weird false combinations. 5NF goes even further, breaking down really complex 3-way relationships to prevent some very subtle but nasty data bugs down the line.
And now for the magic trick. We have spent all this time meticulously taking our data apart, organizing it into these perfect little tables. Now we have to prove that we can put it all back together again, flawlessly.
And this is the #1 question people ask. We had 1 table, now we have 3. Isn't this just more complicated? It's a fair question, but the answer is a resounding no. What we've actually done is made the system way more powerful and flexible. And here's the proof.
The assignment's final test, the moment of truth, is what it calls the reconstruction query. It's a command you give the database using something called joins to pull all the information from our separate tables and perfectly rebuild that original spreadsheet view we started with.
The join is the magic glue. It's how our database knows how to stitch the story back together, linking the rates table to the demographics table and the time dimension table. This one query proves that our whole process was lossless. We preserved every single bit of information, and we can get the exact same results as we would have from the original messy file, but without any of the underlying problems.
So what's the bottom line? We end up with a system that has 100% data integrity and can perfectly replicate any query you could throw at the original data. It's infinitely more robust and reliable on the inside, but it can still give you any view of the data you need on the outside. It is, truly, the best of both worlds. Which leaves us with one final, big question to chew on. We've seen just how powerful and logical this clean, normalized structure is. So why? Why does so much of the data in the world start its life as a simple, messy spreadsheet? What does that tell us about the trade-offs we make between something being easy to start versus being reliable in the long run? Definitely something to think about.